for this section here, we are talking about scientific notation. This is often used in science, especially for things like physics and astronomy, where you're talking about like, distances and outer space, millions and millions and millions, the numbers are so large, like how many atoms are in the sun, those types of things. Or on kind of the molecular level, like in chemistry is often used. I mentioned atoms, but like electrons and stuff like that for very, very small things. So basically what we're looking at is if whenever you multiply by like 10 or 100 or 1,000, things like that. So like, for instance, this would be like 5 times, 10 to the fourth power would be 10 times 10 times 10 times 10. So 10 times 10 would add a 0, times 10 would add a 0, times 10 would add a 0. So you would have like 4 zeros, 10 times 10 times 10 times 10. So 10 to the fourth. And then when I multiply that, then that would just be 5 times, 10,000. So I would add those 4 zeros. But really, we think about it with that exponent. That's just going to tell you how many places that that kind of decimal moves. Because it was, say, here after the 5, and it moved 1, 2, 3, 4 places to the right. However, if I was multiplying by a negative exponent, then that ends up just moving it places to the left. So I have a 5, and then the decimal point would be like 5.0 or whatever, but this time the decimal would move to the left, 1, 2, 3 places to the left, and then fill in those gaps. So notice here it's not like 3 zeros, it's 3 places, one of which covers the 5, and then 2 more get filled in as zeros. On the other hand, let's try to convert this. You got to think like, I wanted to get this number here to be like 4.3 times 10 to the, we got to count them out here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So you had 9 zeros plus the 3. So that was a power of 10 places that it got moved. All right, this one here, the 496, we want that to be a 4.96. So get that to where it's like a single digit number followed by a decimal. So as opposed to 49.6, the scientific notation, we want that number to be between 1 and 10. So like less than 10, like a single digit number. All right, how many places? This one, it's a little tricky. I'm going to zoom in, might be easier for you to see as well, easier for me. So I'm thinking this moved 1, 2, 3, 4, 5, 6, 7, 8 places. And so if I count that up, just to be sure, I got 1, 2, 3, 4, 5, 6, 7 zeros, right? And then the 8th place is to get it past the 4. So this would be 4.96 times 10 to the negative 8. Let's do a couple more of these. So notice this time, wait a second, that's 20 times 10 to the 4th. I want that to be a 2, right? 2 times, it says 20 times 10 to the 3rd. Kind of accidentally said the answer there. 20 times 10 to the 3rd. You could think of that 20 as being like 2 times 10 to the 1st, and then times 10 to the 3rd. And so you end up getting 2 times 10 to the 4th. So you kind of have to move that one extra one there to get that decimal between the 2 and the 0, giving it a total of 4 places that it moves. This one would be kind of similar, right? You got 2 places times 10 to the third. So that would be 2 times 10 to the, can you think of what it is? It would be to the 5th power, right? 2 places for the 200, and then 3 more places for the 10 to the third, so a total of 5. All right. Now, this next one, now we're working in the negative direction. Let's map this out. So if I had done 0.04 times 10 to the fourth, that decimal place, 0.04, that decimal place would have to move 1, 2, 3, 4 more places that get filled in. But in order to make this proper scientific notation, I need that 2 more places to get that decimal to be a 4 times 10 to something. So how many places would that have been to the left? Well, you had 10 to the negative 4, so that was 4 places, but then 2 more places for the 0.04 to make that a 4, so that would be to the negative 6. The next one, this one's even tricky too, because I've got a positive exponent, and so I'm kind of moving both directions, whereas the one above, right, I was kind of getting that to move all in the same direction. So let's map this out again. 0.04, and then that would be times 10 to the 6th. So that would be 1, 2, 3, 4, 5, 6 places that have to get filled in. But in order to make that scientific notation, I want that decimal, right, to be after the 4. So to get that number from there, it would have to go 1, 2, 3, 4 places to get out to the end. So that one's a little tricky because you're working in opposite directions. Okay, so that's kind of just the basics of writing numbers in scientific notation. And then here's doing some calculations. This is actually 2 good examples showing like the benefit of it. Because if I'm multiplying this out, I'm going to get some super giant number. Whereas if I can just do this in scientific notation, I can kind of consolidate what I'm going to be writing. That first one would be 6 times 10 to the 2, 3, 4, 5, 6. 10 to the 6th times 5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So then that's going to give us 30 times 10 to the 16th. But in order to make that proper scientific notation, I need that to be a 3 times 10 to the, well, let's see, I've got to get 16 places to the right, and then 1 more for that 0 there. So that's going to be a total of 17 places, 3 times 10 to the 17th. So notice that's going to be a huge, huge number, but I'm able to write it in this kind of compact way. All right, and another one similar to that, a little tricky. I'm going to have to zoom in to see my zeros. So I know it's going to be a 4.5 times 10 to the negative something. So let me count my zeros and then how many places it's going to move. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So to the negative 10. And then this one would be times 2 times 10. This one's positive. 1, 2, 3, 4, 5, 6. So in this case, you got 4.5 times 2, which actually is 9. And then times 10 to the, well, we would add the exponents. So negative 10 plus 6. So 9 times 10 to the negative 4. So notice the smaller number, that 0.000045, was smaller than the 2 million was big. So that's why this ends up being a small number. If you wanted to think about what that number was, that would be 0.0009, right? A very small number. 1, 2, 3, 4 places to the left. Okay, this one here, kind of a similar thing, except it would be with division. So 1.2 times 10 to the, what would that be? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places over 2.4 times 10 to the negative 1, 2, 3, 4, 5, 6, 7 to the negative 7. All right. So 1.2 divided by 2.4, that's going to be a funny answer. That's a 0.5. 0.5. And then this one here, remember if it's division, you subtract the exponents, but this is kind of a funky one because it's 10 minus negative 7 because you're subtracting a negative. So that ends up being 0.5 times 10 to the 17th. But I need that decimal to be after the 5. So to get out 17 places from the 0.5, well, it would only take me 16 places from after the 5, because one of those places was already taken care of. So 5 times 10 to the 16th. All right, a couple word problems here just to kind of think like some situations this might come up. So Bill Gates' net worth is estimated to be $105.7 billion. Suppose that Bill decides to play the lottery against all odds, wins $40 million. Okay, so he won $40 million playing the lottery. Now express his new net worth in scientific notation. Okay. So $105.7 billion, that would be 105, let's see, 7, and then that's, well, 105 billion. So the comma would be there for the billions, and then 700 million, thousands. Wow, yeah, so that's a big number. That's the billions, right? Right there's 100, 100,000, million, billion, 105 billion. Yep. But then he wins 40 million. So 40 million. All right, so you add that up, that's giving us 105, 740 million. All right, and so putting that in scientific notation, that would be 1.0574 times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times 10 to the 11th. And kind of a follow-up, I'll let you kind of try this one on your own, but what if he had won 10 times as much from the lottery? So instead of 40 million, 10 times as much would be 400 million. So it'd be a similar connection, but except that would just be moved over a place and another zero, and then kind of a similar calculation. All right, one last one. This is kind of an interesting one about how fast computers kind of process information. So Google found 33,800,000 results in 0.89 seconds. So boom, like that. In under a second found over 33 million results. Okay, using this, what is the approximate speed of the Google search engine? So that would be results per second. So in this case, let's go 3.38 times 10 to the 1, 2, 3, 4, 5, 6, 7. So that's the results. And then per second, so that would be 0.89 seconds, or actually let's put that in scientific notation as well. Let's make that 8.9 times 10 to the negative 1, just so that way we can kind of do our math in the scientific notation. In fact, I could have done that on the previous example with Bill Gates too. I should have done that. All right, so here we got to divide 3.38. 3.38 divided by 8.9. That would be, and we're just going to do this with a rounded answer, 0.37977. It actually kind of goes on and on. We'll round that at the end. And then this would be times 10 to the 7 minus negative 1. In other words, that would be 7 plus 1, so to the 8th. However, for scientific notation, I want to get that one place over. So let's go 3.8 times 10 to the, well, we would only need 7 places this time because I'm already one closer by putting the decimal after the 3.